Okay, finishing up with lesson 16.8, we're going to use Stoke's theorem, but in the reverse. Let's just say that you were asked to compute the flux of the curl of a vector field F on a surface, given the equation of our vector field F, as noted here in the problem, but S is the sphere that lies inside the cylinder and above the XY plane. Now, first of all, I do want to state that you could find this directly. What you would have to do is really realize that you are finding a surface integral on this part of the sphere, and what you'd have to realize is that the sphere, really we're not going to have a full sphere, quite a bit less. You can see that our phi, as we move to this outreach here, the boundary of the curve that we have for C is as well that's being traced out. Phi, of course, is not going to be spanning from 0 to pi. Rather, we'd have to find that. We'd be converting to spherical coordinates. But look, if I had x squared is plus y squared is equal to 1, I can substitute that in right in here and immediately say that 1 plus z squared would equal 4, and then z squared would equal 3. Of course, I'm above the xy plane, so z would equal this positive square root of 3. Now you might realize that z is equal to rho cosine of phi. So if we wanted to continue this work, we'd say our rho, our radius of the sphere, is actually a 2 here. So we'd have z would equal 2 cosine of phi is equal to root 3. Very quickly you'd be able to see that the cosine of phi is equal to radical 3 all over 2. Phi would have to be pi over 6. So we certainly could convert to polar coordinates, not polar coordinates, I'm so sorry, spherical coordinates. We'd still have to evaluate the curl of vector field F, and we'd evaluate the curl of F, the flux of that on this surface. But there's a better way. There's actually a shorter way. And this is such a powerful tool. Look, C right here, our curve is going to be this boundary where the cylinder crosses the sphere. You can see that because we are on a sphere, we are on the cylinder, excuse me, we have x squared plus y squared equals 1, always. So what about our curve C? Well, our curve C would be x squared plus y squared equals 1. And additionally, we would say that z would be fixed at radical 3, as we had done some work up above. Now, Stoke's theorem says that we can work this problem out realizing that the flux of the curl of F is really equivalent to a line integral. And you can see that's just referring back to what we had originally, the line integral C of F dot dr. So we're going to have to go back and review how to find a line integral over this vector field. So some good review for our final as well. Well, first of all, let's write out our curve parametrically. Generally, what we've done is we've written it out in terms of t. And I hope you can see, because we have a circle for curve C, very quickly we could note that x would equal r cosine of t. Our r would be a 1, so we could just say cosine of t. Our y value would be sine of t. And z, of course, would be fixed at radical 3. These would be our vector components. And very importantly, this would be evaluated for t between 0 and 2 pi. Very often kids might wonder, why aren't you using theta instead of t? First of all, we could. We certainly could. It's just that we traditionally have worked out these line integrals. We've done line integrals earlier, We did them in regards to a parameter of t. Now, some review. What you can see is that to do this line integral, we're going to, of course, say f of r of t dot producted with r prime of t dt. My goodness. And as we work this out, I hope you can see that r prime of t, just taking a derivative very, very quickly with respect to t, we'd get opposite sine of t, cosine of t for our y coordinate, y component. The derivative of radical 3 with respect to t is 0. Well, what about f? Well, as we look at f itself, notice that we're not going to have to evaluate the curl right now. But with f, though, parameterizing this, we can say that we have xz for our I component. Xz would be cosine of t times radical 3, or just bringing that radical 3 out in front, we'd have it just as so. What about our j component? Y times z. Well, we have sine of t for y. Again, z is radical 3, so we'd have radical 3 sine of t. And then for our k component, we have x times y. So that's cosine of t sine of t. So what we need to do right now is evaluate this integral between 0 and 2 pi. And very nicely, what we wind up doing, thankfully, is we can just write this dot product out very quickly. And something nice is going to become apparent. I think you're going to see something really neat happen. By the way, you should also always be paying attention to orientation. That is something to state about Stoke's theorem. Stoke's theorem would have upward notation for its normals, and if you were to take a line integral curve, path C would have to be going counterclockwise. Well, very quickly, if we work this all out, you would get negative radical 3 cosine of t sine of t for my first part of the dot product, plus, well, now I'll have positive radical 3 cosine of t sine of t. Hey, that's interesting. And now look at this very last part, our k components. We have 0 over here. That's just a 0. The integrand is going to collapse to 0. Integrating from 0 to 2 pi of 0 dt is just equal to 0. That's our final answer. We're going to stop right here, but just pay attention to one other issue. Reading this important note, we computed the surface integral by knowing the values of f on the boundary curve C. If we have another oriented surface with the same boundary curve, we'll get the same value for the surface integral. Amazing. So you can have two very different surfaces. That's what this is saying right here. Why is that so important? Well, sometimes it's much easier to integrate over one surface than another. Okay, well, best of luck. We only have one more lesson remaining in the chapter.